All right, hello everybody. Welcome back to some anti-algorithm math. This is the Walter Rudin real and complex analysis construction of Lebesgue measure via the Riesz representation theorem. I've introduced it extensively in the last three videos, so I hope you'll review those before you watch this. So unless what's on the screen right now makes complete sense to you, in that case, buckle up. You can probably hang in there. But I wanted to start out by showing you um, the um, the statement of the theorem that we're going to prove. And I did the uniqueness last time, which is what I've highlighted here. So that was last time. So what we're going to do this time is prove everything else. So we're going to construct mu and m, the sigma algebra, and the measure. And then we're going to prove all the properties, not exactly one by one. The way the proof goes is a bit scattered, but I'll try to announce to you along the way when we reach certain steps. And after we do the construction, the proof will proceed in 10 steps. So that'll give you an idea of how far along we are. Okay, so so let's get into this. So first thing to do is we're going to do the construction of mu and m. Okay. All right. So this has a lot of stuff that we have to refer back to constantly in the proof. So I want to label everything I can here. So V is open. Open subset of X, obviously. X is our LCH space. All right, so when I talk about an open set, I'm talking about a subset of X that is open, meaning it's in the topology on X, which also happens to be locally compact Hausdorff. I talked about that before. Okay, so we define the measure of V to equal the supremum of lambda f, where f is less than v. So this notation here was covered in, I think, part two, if I remember correctly. And basically, it just means that the support of f is contained in v. So all the values where f is not equal to 0 are contained in v, as well as the closure of that set is contained in v. Also, f is between 0 and 1. So what you should have in mind here is right. So what that means is outside of v, f the function f has to equal 0. Okay, and it's between 0 and 1. So what you should have in mind is, we want the indicator function of v here, right? Somehow that's the one that really gives us the measure of v. But we can't have the indicator function of v because that is not a continuous function. Okay? So, and it also may not have compact support, right? Depending on v, right? So that's why we have this, because we insist that f be a continuous function with compact support, and that support has to be contained in V. Okay, and that allows us to get up to V from here. But I think the intuition here is important. Just remember that this lambda f in our primary application of this theorem is going to be the Riemann integral. Okay, so imagine taking all continuous functions with compact support, where that support is contained in an open set V, and taking the supremum of all integrals, Riemann integrals of such functions, right? If you think about that hard enough, you'll see that that actually does give you the measure of the open set. I will be able to show you an example of that later. Once we go through this proof, I want to demonstrate for you how we know that the measure of the interval from 0 to 1, for example, is 1, right? The length of the interval. Okay. So anyway, uh, we are defining this, okay, mu on open sets, okay? Initially, that's what we're doing. Okay, it's you got to keep track of all this because it gets slightly convoluted. Okay. Um, uh, if so note that if V1 is contained in V2, then the measure of V1 is less than or equal to the measure of V2, right? So um so this measure is increasing. So that means that we can define the measure of E to equal the infimum of the measures of V where E is contained in V and V is open. Okay. And this is for any subset, any E contained in X. Okay. So this this definition will apply to any subset. I'll actually do this here. Okay, a little color coding for you. All right, so that applies to any subset. This applies to V open. Okay, so the point is that this definition is consistent with the previous one because if E itself is open, right, then the measure of E, according to the first definition, will be the infimum, right? It'll clearly be the greatest lower bound, right? Okay, so uh, so this actually applies to any subset. So we do have a measure definition for every subset. The terminology is a little confusing here. That doesn't mean that every subset of X will be measurable. Okay. It's just going to have a measure, but that doesn't mean it's measurable. That's a weird thing to say. Yeah, it just means that it's not going to be in the sigma algebra because we have not constructed the sigma algebra yet. We're actually constructing the measure first and then the sigma algebra, which is weird, but that is how this proof works. Okay. Um, and the property of a positive measure, the key one we need, the countable additivity, right? That I went over way back when. That might have been part one even. I guess it was part two. Yeah, it was part two. Whatever. God, my memory's bad. Um, the key property of a measure only applies on the sigma algebra, so you can't use countable additivity on all subsets. Therefore, like fundamentally, all subsets are not measurable, even if we have a defined measure. This is a little bit like an outer measure, actually, if you think about it. Okay, so now we're gonna let MF be the class of all E, where E is a subset of X. Um, uh, and uh, the measure of E is finite, and the measure of E is equal to the supremum of the measures of K, where K is contained in E and K is compact. Okay. And then I guess I better close the outer braces as well. Sorry that that's so messy. I kind of ran off the end here, so let me try to fix that a little bit. Okay. So this is the small braces, and then this is the big outer braces. Okay, so MF is the collection of sets that satisfy these three conditions. Okay, so MF means we have this, and this. Okay. Um, so uh so that's not quite the sigma algebra, but we're going to use this to define the sigma algebra. And I think the key thing you should note here is that the measure of E has to be finite to be in this. So this can't be the sigma algebra, right? We want to allow sets that have infinite measure. So now what we're going to do is let M be the class of all E so that E is a subset of X, of course, and E intersect K is in MF for all compact K. Okay, so this at last is our proper sigma algebra. Okay, so oops, it's not what I wanted to do. Let's try that again. Here we go. Okay, so these conditions are what allow us to actually be in the sigma algebra. Okay, so now if you think about it, we have a definition of the measure mu, and we have a definition of M, the sigma algebra. So what we need to do now is we need to prove that mu is a measure and that M is a sigma algebra. So, there's axioms. I did go over those. I believe that was in part two, if I remember right. Um, right? So we need to prove countable additivity for mu, and we need to prove the closure under countable unions and complements, and we need to prove that the whole space is in the sigma algebra M, right? So we have all that. And basically this other stuff is going to be ancillary stuff that will help us to generate the thing that we need. Or to prove the properties that we need to prove. Okay, so I want to make a few initial simple observations. Okay, observe. Oh, I just changed color. I don't know why. Um, I wonder if there is an easy way to change color. I haven't figured that out yet. Well, whatever. I'm gonna leave it like this. So observe that if A is less than B or contained in B, subset of B, then mu A is less than or equal to mu B. Okay. Uh, so, that just goes back to this is the definition of the measure, and it's the infimum of the measures of the open sets, right? So, basically, like if you use a smaller set here, it's just going to have a smaller set of these, right? And therefore, um, or a larger set of these is what I should say, right? Uh, every open set that's contained in the larger one is contained in the smaller one. Here, let me point. So if you have an open set that contains B, then it also contains A. Okay? So yeah, I feel like what I said was literally false, but this shows you that um, that the set here for B will be smaller than the set here for A. So if you take an infimum of a larger set, you get necessarily a smaller infimum. I mean, it doesn't have to be strictly smaller, but it's guaranteed to be less than or equal to because it's a greatest lower bound for all the same values and more, right? So that monotone thing is pretty easy to show. Um, if the measure of E is equal to 0, then so uh, let's look at this. So let's say the measure of E is equal to zero, right? We have this, and if you think about a K that's contained in E, right, by the monotonicity, the measure of K would have to be zero as well, right? So as long as there exists, as long as there exists a compact set that's contained in E, um, you know, there's no problem there. Okay. So that might be a question, right? So how do you know that how do you know that there is um how do you know that there is such a compact uh how do you know that there is such a compact K? Well, um I guess a simple thing to say would be that in a locally compact Hausdorff space, points are compact, right? Finite subsets are compact. So if you just take any, well, actually, the empty set's compact, so I don't even need to get that fancy, right? The empty set's compact, and it's contained in, and it's contained in, and it has measure zero, obviously, right? So anyway, empty set takes care of the problem. All right, sorry, too much fretting. Right, so if the measure of E is equal to zero, then uh, E is in MF, right? So notice again, it satisfies these three conditions, right? And if you intersect it with a compact set K, it'll be a subset, right? A subset of E. And therefore, it's going to satisfy all of these as well, right? The measure will still be zero. So if you intersect it with a compact set, the measure will still be zero. So it's still in MF. And so we actually get that it's in M as well. And therefore, E is in M as well. Okay. So all sets of measure zero are in the sigma algebra M. Okay. So that right away actually tells you something about the Lebesgue sigma algebra, right? If if uh, if you do this, right, and you get an infimum of zero, that's in the sigma algebra, right? Okay. So that means, for example, that every subset of a set of measure zero is in the sigma algebra. That's a powerful, I mean, that's an observation that you can use if you want to construct a function that is Lebesgue integrable but not Riemann integrable. Okay, so we have this, and therefore E holds. All right, so let's remember what E was. So this is E, right? If E is in M and A is the subset of E and the measure of E is zero, then A is in M because the measure of A is also zero. So right? So actually like part E is done now. Okay. So I'll just check it off. All right. Um and eh, I guess I'm not entirely happy that I checked it off like that. Oh well, whatever. It's probably fine. Okay, so therefore E holds and um and C holds. Okay. So why does C hold? So this is C, okay? So C here actually holds by definition, right? If you just look at the definition of the measure, right? That's exactly what C says, right? And this is actually true for any E. In particular, it's true for the E in the sigma algebra M. Okay? So C holds by definition. Okay. So therefore E holds and C holds. Um, okay. And let's also observe that lambda is monotone by positivity. Okay. If um, F is less than or equal to G, then G minus F is positive. Okay. And and that means that lambda of G minus F is positive. Okay. So because we have a positive linear functional, so let's not forget about that um, little condition. Okay. Positive linear functional. All right, that matters here. Okay, so now we have this, and therefore by linearity, lambda of G minus lambda of F is greater than or equal to 0, and therefore lambda of G is greater than or equal to lambda of F. Okay, so yeah, sorry it's facing the wrong way. This is the same as G is less than or equal to F. I don't think that's sorry, greater than or equal to F. I don't think that's something I need to tell you if you're actually watching this, but let's just say from teaching math, I know a lot of students get confused about flipping around an inequality, like 1 is less than 3 and 3 is greater than 1, right? That's all I'm doing here. Okay, so anyway, we know that lambda is monotone. So this is, according to Rudin, this will be used in steps 2 and 10. Okay. So so when we get to step 10, we should come back to this and we just need to remember that lambda is monotone. Okay. All right. So we have now constructed mu and m. Okay, we haven't proven that M is a sigma algebra. We haven't proven that mu is a positive measure. We haven't proven that it represents the function lambda, the functional, the functional lambda. We haven't proven that finite sets, or sorry, we haven't proven that compact sets have finite measure. And we haven't proven that if E is open or E is in M and has a finite measure, then it's equal to the supremum of the measures of K, where K is compact and contained in there. Um, we do know by definition that that uh, well, we have this. I mean, if you take the combination of the two here, you can see that the second part is clearly true, right? So E is open is really the key thing that we still need to prove there. So the rest of this we're just going to prove along the way. All right, so let's dive into a step here. Let's start with step 1. So step 1 is going to be mu of the union. Sorry, I should not have written it that way. Mu of the union I equals 1 to infinity of AI, or EI. I don't know why I don't have to stick to Rudin's notation, but I just think for my own sanity, I'm going to, is less than or equal to the sum of the measures of the EIs um, for EI any subset of X. Okay? So this is like half of countable additivity. Okay, so this part, again, I think this suggests we're looking at something like an outer measure here. I'd have to review the definition, but I think this is sort of the idea of an outer measure. You have this like sub-additivity, right? You don't quite have additivity, you have almost additivity. Um, okay. Of course, I didn't insist that they were disjoint. All right, so let's start proving step one. Okay, first, we show that mu of V1 union V2 is less than or equal to mu of V1 plus mu of V2 for V1 and V2 open in X. Okay. So we want to end up getting this for a countable number of arbitrary subsets, but what we're going to start with is proving that it's true for two open subsets. Okay, so it's a special case. All right, choose G less than V1 union V2, right? The union of two open sets is open, and we can use the Eurozone um, lemma. Uh, the subtitles has no idea what I'm saying when I'm saying Eurozone. So let me just, I'm just gonna write what I'm saying there. It's spelled like this, UrYSOHN. That's Eurozone. Okay. I'm not talking about the Eurozone here. Okay. You know, AI is so smart, and yet sometimes it just seems to have no idea what the context is. Okay. So we choose a G. So this means that G has compact support and it's between 0 and 1 and the support is contained in this union. Okay. Um uh by partition of unity, I think I did partition of unity in part 2, if I remember right. So by partition of unity, there exists H1 and H2 such that H1 is less than V1, H2 is less than V2, and um, H1 plus H2 equals 1 um, in the support of G, which is compact, right? So when I use this notation, there's an embedded assumption that G has compact support. So that is our compact set K, okay? Um, and we know it's contained in V1 union V2. And so then we can apply the partition of unity theorem, which I talked about before. Okay, so uh, hence, um, hi times g, hi times g is less than vi. Okay, so you might have to think about that for a second, right? If this is not equal to 0, then they both have to not equal 0. So the support of this is contained in the supports of each one. Boom, boom. Okay? So it's contained in the intersection. I mean, it's contained in the support of each one. And therefore, in particular, it's contained in the support of HI, and therefore we get this. Okay. Um, and G or H1 G plus H2 G, and this is times, by the way, not composition, is equal to G. All I'm doing there is multiplying this equation through by G. Um, And this is for all x in x. Why is that true for all x in x? So I know this equation is true in the support of g, which is where g is not equal to 0, right? It's actually larger than that, but all the points where g is not equal to 0, this is true. So we have this. If x is not in the support of g, then g of x is equal to 0, and I get this also. Okay? Okay, so even though I don't have this equation for all x, I do have this equation for all x, which is pretty cool, I think. Okay, so we have that lambda of g is equal to lambda of h1 times g plus lambda of h2 times g, just using basic linearity. Okay. Um, and remember the definition of the measure of an open set. Okay, so it's this. It's the supremum of the f's that are less than that open set. And we know that HIG is less than VI. So each one of these is then less than or equal to the measure of the corresponding open set V. So we get this. Okay, and this holds for any g less than v1 union v2. So that means that if we take the supremum, right? So again, let's go back. It's the supremum of these, right? So the measure of the union is the supremum of the functions that are less than that union. So that means that the measure of v1 union v2 is less than or equal to mu of v1 plus mu of v2. Okay? Because we can just take the supremum of all of these, which are all less than this. If they're all less than this, then, you know, then the supremum is, right? So boom. Okay, so that takes care of the two set version. Okay, so we'll do my blue check mark here for that. Okay, now uh remember what we want to show in general is this. Okay, so all we have for now is it works if we have two open subsets, and that's it. Okay. Okay. Now observe if uh if the measure of EI is equal to infinity for some I, then the result is clearly true. All right, let me just explain that. Okay, so if the measure of one of these is infinity, this sum is infinity here. Anything's less than or equal to infinity. Okay, done. Now, in fact, this will also be infinity. It's just infinity less than or equal to infinity, which is fine, right? We're allowing that. Okay. So that means we can actually assume that the EIs all have finite measure. So let's go ahead to a new page and do that. So now assume without loss of generality. Okay, that's what WLOG stands for, without loss of generality. Um, that the measure of every EI is finite. Okay? Okay. Now let epsilon be greater than 0. We're just picking an arbitrary epsilon. We're doing analysis here, all right? And this isn't non-standard analysis. I'd love to do a separate video on that because I actually want to learn about that myself, and that could be a way to help me learn. Anyway, requests encouraged as always. So let epsilon be greater than 0. Um, by um, by definition, so the definition I'm referencing here is this one, okay? This is the general definition of the measure of any set, right? So we can approximate the measure of any E from above by open sets, right? So if this measure is actually finite, then we can find an open set that's actually finite and as close as we want to this, okay? So I'm going to get, within epsilon, not exactly epsilon, but any epsilon I want. So I'm going to choose a special epsilon because we're playing games with epsilons here, right? And that's something you're allowed to do. It does seem a little silly to me to play games with epsilons here, but that's what we're going to do. Okay. So by definition, there exists open um, VIs containing the EIs such that the measure of VI is less than or equal to the measure of EI. So I could say plus epsilon here, but Rudin doesn't want to say plus epsilon because remember, what we want to do in the end is add all these together. Okay, so we don't want to be adding epsilon to itself infinitely many times, or that value is going to get out of control. So we control it with an extra factor that we're allowed to put in because we can do this for any epsilon. Okay, so specifically what we're going to do is epsilon over 2 to the power I. Okay? Okay. So, I mean, this is generally smaller than epsilon. Okay, but the nice thing is this is getting smaller and smaller as I increases, and I'll be able to add these up and I won't exceed epsilon. That's really the reason why we're doing this. This is a classic trick in analysis. Okay. Now let V equal the union of the VIs. I keep writing the letter U, but I mean to write it like a union. Okay. Those open sets we just chose and choose um, F less than V. Okay, so you should know what to expect at this point, right? Remember the definition of measure for an open set is like this, right? So we want to take this back to the positive linear functional, right? And so we're passing from an arbitrary subset to an open one, okay? Okay. So we choose F less than V. Since F has compact support, right? So compact support. Okay. Um, that means the support of F is contained in a finite number of these VIs, right? So the definition of compact is that every open cover has a finite subcover. This is a cover of the support of F, which is given to be compact. So that means the support of F is actually contained in finitely many of these V's, which means that if I take the union out far enough, it will have to contain the support of F. I don't need all of those V's necessarily, but just notationally it's friendly to do that. So since we have that, we have F less than the union I equals 1 to n VI for some n. Okay, so that just comes from the compact support. Okay, now applying induction to previous inequality. So let me just remind you what that was. So that was this one. Okay. So just so you know, let me talk it through. Induction is very common. If you're watching this video and you don't know what induction is, again, no shame. No one's born knowing what induction is. But You really should have seen it by now if you've reached this. Okay, so you probably know, but if you don't know what it is, basically it's a way of going from a statement like this, that's just about two open subsets, to any number, right? So if this is true, we can then sort of leverage that to say that this inequality holds for any finite collection of open sets. Okay, so if I have a finite union here and finitely many of these here open, then I get this inequality. So that's what I'm going to apply now. So applying induction to that inequality, we get that first of all, um, lambda f is less than or equal to the measure of the finite union. Okay, that's just by the definition. Okay, remember this. We're just using that again. Okay. And now the induction is really giving me this inequality here. It's less than or equal to the sum I equals 1 to n of the measures of the individual VIs. Okay, and now remember the measures of the individual VIs are less than or equal to these. So what we get then is sum I equals 1 to n of mu e I plus epsilon over 2i. Okay, so we're summing all of those, but then, I might as well just sum all the way out to infinity, right? That's only going to make it larger. Okay, and so this is where you might need to know some stuff about infinite series, like geometric series and stuff. So now this is equal to the sum from I equals 1 to infinity of mu e I separated now plus epsilon. So the sum of all these is equal to epsilon. Okay? And that's something you should be able to prove. Or it's less than or equal to epsilon. I guess I'll say less than or equal to because I don't want to think about it that hard. But no, the more I think about it, the more I think it is actually equal to epsilon. But I don't really care. The point is it's less than epsilon for sure. Basically because the sum from I equals 1 to infinity of 1 over 2 to the I is less than or equal to 1. And you can show that yourself if you want. There's an easy picture to see it too, if you want, right? It's a half plus a fourth plus an eighth plus a 16th. And if you think about it, you can keep doing that forever and you're never gonna get to one. Now, the sum is actually equal to one in the end, but really the less than or equal to is all I need here. Okay, so um, so I just proved, let me let me highlight a key point here. I just proved this is less than that um, for any f that's less than v. And so that means then that the measure of v. So remember, v is the full union, right? Not just the finite one. Okay. So, but since this holds for any f that's less than v, that means it's going to hold um, for v. So the measure of v is less than or equal to this exact thing. Measure ei plus epsilon. But of course, that union here, remember the vi's contain the ei's. So that measure is less than or equal to the measure of the union of all the ei's. Okay, and now we can see that this is less than or equal to that for any epsilon. So we can let epsilon go to 0 and we get the inequality that we wanted to prove from the start, right? So so that is the final step here, right? So what we wanted to prove was this. We prove that this is less than or equal to this plus epsilon for any epsilon. Therefore, this is less than or equal to that. Done. Okay, cool. So that's step one. Shall I do step two? Do I have time? Let me try to get through step two before I close this video out. It takes it takes time to get through this. It's a long proof. Okay. So let's go on to step two, having finished step one. Okay, so step two. Step two will be if K is compact, then K is in MF, and uh, the measure of K is equal to the infimum of the lambda F's. You should be able to guess what I'm going to say here if you're following this. What am I going to say? What am I going to say? The F's greater than K, right? That's the key trick we're using. And by the way, once we finish this, this will imply B. Okay? Why will it imply B? So remember what MF was? MF was a set of subsets that have these three properties. One of those properties is finite measure. And part B is just that a compact set has finite measure. So when I'm done with this, step two, we will have completed B here. Okay? So we're slowly chipping away. Okay. Uh, there we go. All right. So if K is compact, yeah, so this is what we're going to prove. Okay? So let's do it. Proof. All right. If uh, K is less than F and we'll pick an alpha between 0 and 1. This is a funny little trick that Rudin does. Rudin actually wants to let alpha approach 1, but he wants to pick something less than 1. I believe I did a trick like this in a previous proof. Uh, was that monotone convergence? I want to say that was monotone convergence. I don't, there was a trick like this before. Anyway, so we have this alpha and we let um, V alpha be the set of all x um, such that f of x is greater than alpha. Okay, so that's V alpha. Okay, um, and by the way, um, uh, f is a continuous function. Okay, so these are open. Just FYI, right? Because f is a continuous function, these are open. Okay. Then um uh then K is contained in V alpha. Okay, so why would that be true? So K less than F means that F is equal to 1 on K. Okay? And since alpha is less than 1, all the points of K are in here. Right? That's it. Okay. Fairly straightforward. And alpha times G is less than or equal to F whenever G is less than V alpha. Okay, so let's try to understand this. Okay, so if the support of G is contained in V alpha, okay, uh, then uh, then that means that if that means that if G is not equal to 0, okay, that means if G is not equal to 0, then f of if G is not equal to 0 at x, then f of x is greater than alpha, okay? And alpha times g, right? Remember, g here is between 0 and 1. So this is guaranteed to be less than or equal to alpha all the time, and f is greater than alpha, okay? According to this, okay? Um, uh, if sorry, and so that holds if g of x is not equal to 0. If g of x is equal to 0, this inequality is trivial. Okay, so yeah, maybe I should actually should I spell that out? I almost feel like I need to spell that out here. Um, yeah, let me this is sort of commentary, but I feel like that's what you're here for. So if g of x is not equal to 0, then um, x is in the alpha. So f of x is greater than alpha, which is greater than or equal to alpha times gx, right? Because gx is less than or equal to 1. Okay. All right. So this condition, when you write down this less than, it implies that g is between 0 and 1. Okay, so if you know that, then you have this automatically. So you have this. Okay, if g of x equals 0, then alpha times g of x equals 0 is less than or equal to f of x for sure. Okay. So in either case, there's no problem. Those are easy arguments, but I just wanted to fill those in for you. Okay. So now, uh, because we have that, we get that the measure of k is less than or equal to the measure of v alpha. Okay. And that's just because k is a subset of v alpha. Okay. Now, V alpha is open, so this is equal to the supremum of all g's, so that g is less than V alpha. Okay, so uh, so that means, flipping this inequality, which we have here, right? Flipping that inequality around, we get that g is less than f over alpha, right? G is less than f over alpha. Okay. So, and that's true for all g. Okay. So, so that means that this is less than or equal to um, lambda or 1 over alpha lambda f. Okay. So remember the monotone thing? Okay, so I mentioned that back here. So lambda's monotone, okay? It preserves the order, okay? So if I know that that g is less than or equal to 1 over lambda times f, then I know that oh, I messed up. I forgot my lambda here. All right, let me fix that. Lambda goes there. Okay, cool. So so lambda of g is less than lambda of f over alpha, right? So like you could literally rewrite this as 1 over alpha times f, okay? Because alpha is not equal to 0, okay? So I'm allowed to do that. Um, and then the 1 over alpha can be pulled out of the linear functional by the linearity properties. Okay, so we get this. All right, and we get this for any alpha, okay, between 0 and 1, right? Those are the conditions on alpha. So now we let alpha approach 1, and we get that mu of k is less than or equal to um, lambda f, which by the way is finite. Okay, so that's part B. Okay, so what I just did there, I'm not finished with this part yet, but what I just did there takes care of part B here. So let me go ahead and celebrate that victory because we just proved part B. Okay, so now let's go back. Okay, so now we have this. So we know the measure of k is finite, and let's go back to what the definition of MF is. So we know the measure of k is finite. We know this. This clearly holds, right? If E is compact, right, by the monotonicity of the measure, and that means that uh, K itself will serve as the least upper bound, right? The supremum, right? If you start out with a compact set, then that compact set will approximate it as well as possible, right? The measure of it as well as possible. Okay, so uh, and clearly then K is in MF. Okay, and let's just remember what I'm trying to do here. If K is compact and K is in MF, I already got that. Okay. And so we have one more thing to prove. So now I want to prove that it's equal to the infimum of the lambdas where uh, uh, lambdas on functions who they're continuous functions with compact support between 0 and 1, and um, f is equal to 1 on k. Okay, so they're like quasi indicator functions for k, right? They're not literally, but they're like, that's how you want to think about them, right? That's how we're kind of operating with these things. Okay, so K is in MF. So now we want to prove this last property. Okay. So now um so now if oops, oops, let's try again. There we go. Now let epsilon be greater than 0. Okay. There exists V um V open. So open contained in K such that um, the measure of V is less than or equal to the measure of K plus epsilon. I can make that a strict inequality if I want. So I guess I'll do that. It doesn't really matter. What am I using here? I'm just using the definition of measure. Okay, so this applies to any subset. Okay, I can always do that. Okay, and now, as soon as you have this, you should think, oh, now I need the Eurozone lemma. So by Eurozone, so by the Eurozone lemma, um, uh, there exists an F that is trapped between K and V simultaneously. Okay? So that's what we get out of Eurozone. Thus, uh, lambda of f is less than or equal to the measure of v, right? Because v is open, which is less than the measure of k plus epsilon, okay? Okay, and so that means that we can get as close as we want to you know, to the measure of k, right? So the point here is we can approximate the measure of k with open sets, and we can actually go below any open set with a lambda f. Okay, so these mu v's are converging to the measure of k. That means these lambda f's have to be converging to the measure of k as well. Okay. Um, okay. Okay, right. So, so therefore, um, because, all right, let me, okay, we got this. The measure of k is less than or equal to lambda f for any k less than f, including this one in particular. And we can get as close as we want from above, right? We know these are all greater than or equal to mu of k, but also we can get as close as we want, right? Because we're within epsilon. Okay. So now we let um whoops. Now we let epsilon go to 0 and we get um well no, that's not really accurate. Whatever, it's close enough. And we get that the measure of k is equal to the infimum of the lambda f's where k is less than f. Okay, all right. So we know all of these are greater than that by this condition here. And we know that this is less than mu k plus epsilon, where epsilon is arbitrary. So that means we can get as close as we want from above to this. So the infimum here has to be that, because all of these are greater than or equal to that, and they also get as close as I want to that. Okay? That then ends the proof. All right. And we got a dog bark, so I think that's a good time to end. So so I will come back um, in the next part and prove as many more steps as I can. We'll see how long it takes. But anyway, thanks for hanging in there with me, and I will see you on the next one. All right, bye everybody.